Hello, everyone. In this video, we're going to continue our work in section 8.2 and look at a formal definition of geometric series and then finish off with example 2. All right, so in example 1, we saw an infinite sum that we called Q. So here I have it written down here as well. So in mathematics, when we're considering an infinite sum of any sort, we call it a series. So Q is an example of a series. It is an infinite sum. It is created by adding up an infinite amount of terms. In particular, we can notice that this series has a certain pattern, and that is when we move from term to term in this summation, we're multiplying by the same number each time. So to get from this first term to this next term, we multiply by 0.1. To get to the next term, we multiply by another 0.1. To get from our third to fourth term, we multiply by another 0.1. So series of this form that have a particular pattern are called geometric series. Geometric series. So let's look at that formal definition in the box on our workbook page here. So if we let A and R be constants, then the infinite sum, so we're adding up an infinite amount of terms that look like A times R to the N, where that exponent goes from 0 to infinity. So what does that look like? Well, that looks like our first term is when N equals 0. So that would be A, R to the 0. But R to the 0 is just 1. So that would just look like A. Our next term, when N equals 1, would be A, R to the 1. When N equals 2, we have A, R squared. When N equals 3, A, R cubed. And we're just adding up like this, adding up these terms forever. Okay, so this is an example of a general geometric series. And here we go. It is called a geometric series. So we have some language for describing some of the terms in the geometric series. So this A here, I'll highlight. This A has a special name. It's not too fancy. It's just called the first term of the series. So A is the first term of the series, and R, this value here, is called the common ratio. And it should make sense why we call R the common ratio. So if we compare any two values here, so if we look at the ratio of AR squared to AR, we see everything cancels out but R. So R is that common ratio in our series. Okay, cool. So the series, so this is now a fact that we're going to use. In a future section, we're going to prove why this is actually true. But now we have some facts about series of this form. So the series has a finite sum if that common ratio R is between -1 and 1. And in particular, we know what that series is equal to. That series is equal to A over 1 minus R. That is it again, if R is between -1 and 1. And in this case, we say that this series converges. What else could R be? Well, R could also be bigger than or equal to 1 or less than or equal to -1. So we can write that in a more compact way by saying the absolute value of R is bigger than or equal to is greater than or equal to 1. In this case, the series diverges, meaning the sum is not finite, it blows up. And we can see why that should be the case as well. If this R is bigger than 1, then each term here gets larger and larger and larger each time. So we're adding up an infinite number of numbers that get bigger each time. So of course, we're not going to be able to add up all of these infinite numbers and get something finite. Okay, cool. So let's just, before looking at example 2, let's just use the language we were just introduced to look at that geometric series that we saw in example 1. So in this case, what's the first term of our series? that would be 100. So A here is 100. And what about R? Where R is that common ratio, it's that value that we're increasing the exponent each time, that would just be 0.1. Okay, cool. So now we know what A and R are for our geometric series from part or example 1. And that's going to be useful in example 2, because example 2 says use the formula for the sum of a geometric series given above to confirm your answer to part B in example 1 on the previous page. So let's go ahead and just write out what that Q was that we were computing. It was an infinite series, K equals 0 to infinity of 100 times 0.1 to the K. So again, we just saw that A was 100 and R was 0.1. So which situation are we in here? Are we in 1 or 2 from the definition? Well, R equal to 0.1 is less than 1 and bigger than -1. So we are in case 1. So this means that we can confirm that Q is finite. And in fact, we can confirm that Q is equal to A over 1 minus R. So what is that for us? Well, A is 100 over 1 minus 0.1. So if we work that out, we get 100 over 0.9. And if we put that in our calculator, you'll see that we get 111.11111. That one repeats. Pretty cool. So go ahead and check your work from example 1. You'll see that we got that same result when we looked at a table of values. So the table suggested we would approach this number. And in fact, using this definition and fact about geometric series, we can confirm that that suspicion we had in example 1, part B was true. So I'll just finish that off by saying this confirms our answer from before. All right, awesome job working through this section.